Hello, welcome back to another video. Today we will continue discussing the database leaking attack, this time against the WhiteDB database implementation. So first off, what is this attack? Fundamentally, it is a data leak attack. We are trying to leak data from the database that we otherwise shouldn't be able to. Since databases are one of those types of targets where merely by leaking data we can get a lot of value. We don't actually need to get RCE in many cases to get anything useful. And about this attack, databases in memory, they will have a model of the database, and that model is what is leveraged in order to perform various operations such as lookups, record insertions, that sort of thing. And when the database process dies or exits out, since that memory will be gone, it needs to store that model somewhere, and in many cases, this one included, it has the option to store it as a file. And the neat thing is the data in that file and the data in memory in the actual database model in many cases will be nearly identical. And another cool thing about this database model is in this one, offsets are used, and it's sort of like what a pointer would be in C. So let's say you have a record and the third field is a rather large string. In this case, instead of actually storing the large string in the record, it will store the large string somewhere else, and in the record it will store an offset to that string, which is sort of like a pointer. And the thing is, the file where the database actually persists, that file can be edited along with those offsets, and I'm pretty sure we all know where this is going. Changing those offsets can lead to some interesting things. For instance, let's say we have a web application where it uses this database as a backend, and as part of the normal web app, we can query a user record, and the third field is the username, which we can see. We can edit the database file so that the third record, or sorry, not third record, third field of a record, instead of pointing to a username, it points to some other piece of data in the database in which that we would want. So then by merely using the web app, we'd be able to leak data that way. Now, I'm sure many of you are probably scratching your head being like, what is the usefulness of this attack? And to a certain extent, that is true. Coming up with actual use cases for this type of attack is going to be rather hard. However, especially because you're probably like, if you can edit the file, you can already see what's in that file, so what good is leaking information from it? And to that, this type of attack, what you can do is you can potentially leak data that is created after you edit the file. So let's say you edit the file, goes into the database, and then new data is created that you want to see, you could leak it that way. And also another thing that's sort of the overarching goal of this entire project is alone this type of attack being useful or actually possible against one sort of database isn't really that much. However, one pattern I'm seeing is several different database implementations is vulnerable to either this sort of attack or similar attacks. And if I can show that this sort of attack is possible against many different database implementations, while the actually using this sort of attack will be strenuous and hard, the amount of possible situations where this type of attack could be deployed would increase significantly. So now a bit about this database implementation. It is known as WhiteDB. It is an older databasing software. I do believe development on it has ceased. And what is it? It is a database API. That means that if you're writing, let's say, a C program and you want database functionality, you would import this project and you could use its various API calls to have databasing functionality. Cool thing about this database implementation is that there is no set schema. So let's say you have a database, you can have 3 records. First one can have 3 fields, second one could have 5 fields, next one could have 10 fields, and you could have a record where the third field is set to a string, and then you could change that to an integer or whatever you want. For this project, I worked against version 0.8, which at this time I believe is the newest version. And if you want to see more, there is the URL for you to check out the project. So now to actually show you what I mean by it being a databasing API, here is a C program that I wrote that uses the API. We can see here that first I import it, then I create the database, then I create the records for the database, and then I go ahead and encode the various values that I wish to insert into the records of the database. Then I go ahead and insert those values into the database. Then I go ahead and dump the records. This sample file was based off of the examples from the project, and also later on in the video I will be in detail showing you the data generated for the records by this file. So next up, we're going to discuss data type encodings. For this database implementation, when you're storing a particular value within a record, it will not simply store that value. It will first take that value, encode it, store the encoded value, and then when it's trying to retrieve that value, it will take the encoded value that is stored, decode it, and that's how it will get the original value. Now, since this attack type relies on editing these encoded values, that's why I'm wanting to understand a little bit about how this data type encoding works. Now, first off, why does it encode them? There are several reasons from what I can tell. So a database record in this implementation is made up of fields. Cool thing about this database implementation that I said earlier is that you can store any particular data type in any particular field, and you can even change that. So let's say I have a record with 10 fields, you can insert a string into field 5, and then you can then later on replace it with an integer. And the first problem that this solves is it needs a way that it can look at a field and tell what data type it is. So part of the encoding process is it will mark specific bits, and then it can then look at those specific bits to check if it is a string, integer, what data type it is. And the second problem that this tackles is the fact that all fields in this database implementation have the same size. I believe for 64-bit systems it's 8 bytes. For some data types like a character, 8 bytes, you can store a character in 8 bytes. However, for other data types like certain types of strings, that isn't enough size. So realistically, some data types or some data might not fit within the fields. Now, first off, how are they encoded? I'm going to be getting into more detail about this in a bit, but basics. First off, if a data type or a data that's trying to store is small enough and can actually fit within the field, it will simply just take the value, mark the bits to signify what type it is, and then store that value in the field. And let's say if you're storing a massive string, how it typically deals with data that it's trying to store that's too large to store in a field is this database implementation has its own custom like memory allocation within the database itself. It will simply allocate space in the DB, store the data that it's trying to store at that allocated space, and then in the field itself, store an offset to that data so it can then look at the field, see that there's an offset, look at the offset to get the original data. But in all encoding types, it will always mark specific bits to signify the type. That way, when it's trying to actually look at the field, it can look at those bits to see what data type it is. So next up, we're going to discuss in detail how this database implementation will actually encode specific data types, starting off with the character data type. To encode it, it will just call the wg encode char function. This right here is a generic database check, and this right here is some logging stuff. What we are primarily interested in is the encode char macro right here, which we actually see that here. Effectively, how it encodes a character is it shifts it over to the left by the char shift constant and then ors it by char bits. You see that char shift, the constant is 8, and char bits constant is ox1f. So it effectively just shifts it over to the left by 8 bits and then ors it by ox1f. And then to decode it, it just shifts it back over to the right by 8 bits. So for an example, let's say it's encoding the value ASCII 0, which has a hex value of ox30. It'll just take ox30, shift it over to the left by 8 bits, and then OR it by ox1f to get the value ox31f. And for the record, this ox1f byte in the lowest byte is to signify that it is a character data type. Hello, so now I want to actually show you an example of a record with characters in it. This over here is the source code file which actually generated the record, and the record that we will be looking at is record 0. We can see that it has 10 fields in it, and in fields 0, 1, and 2, char 0 has been inserted into it, which we can just see is the encoded character 0. Now to find the record, since I know the char encoding algorithm, I know what 0 should be, and I just searched for it. It actually begins at offset OXB 770. Now, one thing about the records I've seen in this database implementation is they have 3 fields of record metadata before it actually has the records which hold the data. Since a field is 8 bytes, that's OX 18 bytes, so the fields that we control don't actually start until offset OXB788. And we see there's the value 31F, 31F, and 31F. It started in least Indian, least significant byte first, that's why the 1F is below the 30. And since we know the character encoding algorithm, which is right here, when you run 0 through it, we see that it gets OX31F. So that checks out. So next up, we will cover the integer data type encoding, which it is encoded using the WG encode int function, which you can see right here. Also, as you can see, I've cut out some parts of the function to sort of summarize it to the bits that I feel are relevant to this, to keep it from being just a giant function on the screen. For integers, there are 2 different types of integers in this database implementation, small integers and full integers. Primary difference between these being, within the field, there are only so many bits that I can actually store in there, and full integers, in order to effectively model the value, you need more bits than the field has. So to check if, full integers are effectively require more data and are larger than small integers. To check if an integer can fit within a small int, it will call the fit small int macro, which you see right here. Small int shift is a constant that is 3, so effectively it'll just shift it over to the left by 3, shift it back over to the right by 3, and then just check if that is equivalent to the value prior to the shifting. What this effectively accomplishes is it checks are the higher 3 bits set, and if they are, then we can't encode it as a small integer without losing some of the value, because to encode it as a small integer, it just shifts it to the left by small int shift and then ORs it by small int bits, which is OX3. So if those higher 3 bits are set, this small int encoding process, those higher bits that are set will be lost and you won't be able to actually store it. So for integers where those higher 3 bits are set, it will allocate a piece of data using the database memory allocation functionality, where we'll actually allocate a block of memory within a database. It will store the integer that it's trying to store at that offset and then return that offset. Now, it will actually encode the full int offset by ORing it with full int bits, which is OX1. Now, the offset actually being stored, it isn't really the correct offset. Reason for that being is because it's being ORed by another value full int bits, which is effectively the type bits. So to decode the offset, it will effectively just clear out those bits, and once those bits have been cleared out, you will actually have the offset to the piece of data that is stored there. Okay, next up I want to show you an actual example of integers encoded in a database record. For this one, we're going to be looking at record 1, which I was able to locate via knowing what char1 encoded is and just searching for its value. This database record begins at OXB7D8, and then we see the fields we control begin at offset OXB750 with offsets being listed right here. There are the 3 char fields, and then we have the first integer. Now in here, there are 2 integers being encoded, int0 and int1. Int0 is just OX50 encoded, which is small enough to be stored as I believe, either a small or a tiny int. And when we look at the algorithm for that, which is just taking the integer, shifting it over to the left by 3, and then ORing it with 3, we see that encoded value should be 0x283, and when we look at that position, we see that that number 0x0283 is there. Again, this is least Indian, least significant byte first. However, for the second integer, we see that there's an offset 0x013750, and this is because the integer that we're storing, 0x deadbeef, is too large for that. So if we go to that byte, 0x013750, we see deadbeef is right there. And with that, we have seen the actual integers being encoded in the database. So next up we have the string data type, which is encoded using the WG encode stir function, which realistically just wraps this function. Now for this is the function right here. I've cut out the parts that I felt weren't relevant to not have a bunch of unneeded stuff on the screen. Similar to the integer data type, there are actually multiple string data types that comprise a string. There are tiny strings, short strings, and long strings. Primary difference between these three data types is just the length of the string. So first off, we have tiny strings. Tiny strings are strings that are small enough that they can actually fit within a field along with the type byte. For the three string data types, it uses the entire lowest byte to signify what the data type is. So for this, it'll just do a size check right there, and if that's the case, it will go ahead and set the lower byte equal to tiny stir bits, which we can see that is OX4F. Then it will copy the string there and return that. Now next up we have short strings, which are longer than tiny strings, but shorter than short stir size, which is 32. Now for this, it will actually allocate a space of memory to store the string in. This is done with allocate short stir. Now with this, all blocks that are allocated for a short string, they are all the same size, but with that, it will then copy the string to that specific data and then encode the offset and return the encoded offset, which we see for encoding it, it will just order by short stir bits, which is OX6. Now for the final string data type, which is long strings, effectively for this one, unlike short strings, it will actually allocate a block of memory that is the size of the string that's being allocated, and then like short strings, it will just simply encode the offset and return it, and we can see to encode it, it just orders it by long string bits, which we can see is 4. Also, one thing that I just wanted to show with this is we see here there's a macro is tiny stir. For all the data types, there's like a corresponding function. This function will effectively check, is this particular value this particular data type that we expect it to be? In this case, what it does is it just takes the value, ands up by tiny stir mask, which you can see is OXFF, so it's getting the lower byte, and then just checking to see at that lower byte, which it expects to be the type byte, is it equivalent to the tiny stir bits type byte. But yeah, that is the data type encoding for strings. So next up, an example of what strings encoded in a database actually look like. For this, we'll be looking at record 2, which begins at offset OXB840. I found this record the same way I found the previous records, and you first have the 3 characters here, here, and here, and then the string offsets begin at OXB870, and the other one begins at offset OXB878. We can see here that there are 2 strings encoded, which come from here and here. Also, in case if it didn't state it beforehand, this database file was created by compiling and running this script over here. And we can see that the offsets for the string are OX011750 and OX011770. The reason why it's not OX011776 is this last OX6 at the end. That is for the data type. As we discussed earlier, it's not actually part of the offset. So when you actually go to those offsets, we see, where does it go to byte? OX011750. We see that there is T, which matches the first string, and when you go to the second one, and we see that string is there. So there we have seen what strings encoded in a database actually look like. So the last data type that we will cover is records, and what I mean by a record is I mean an actual database record. Taking a step back, a record is actually allocated using the same memory allocation functionality that we've seen used for long strings and integers. And effectively in your code when you're using this database, you will have a pointer to the record, and that's how you actually like reference and do things with a particular record. And this function that encodes a WG encode record, you will actually hand it that offset, and that's what I'll use to encode it, and that's the value that actually gets stored. Looking at this function, it relies on the encode data rec offset macro to actually handle that, and looking at it, it just returns the value given to it. This is strange because looking at all of the data types up until now, the encode macro has always ordered in some type bits. However, looking at the isDataRec macro, it kind of explains it. For this, it ANDs it by DataRec mask, which is OX7, so it's getting the lower 3 bits and checking to see if it's equal to DataRec bits, which is 0. So effectively, it's checking are the lower 3 bits of this value equal to 0. And for that, going back to record is allocated space using the same memory allocation functionality. And apparently one feature of that, as I think for alignment purposes, the lower 3 bits are not going to be set in that case. So the pointer or offset that we get from that functionality is already going to have those 3 bits not being set. So we don't need to actually set it when we are encoding that offset. But yeah, that's it for records. So next up, I'm going to show you an example of what a record encoded in a database looks like. For this, we'll be looking at record 3, which its fourth field has rec encoded stored in it, which we look at that, we see it's just record 0 encoded. When we go to the start of the user-defined fields of rec3, we see that there are 3 characters, which is just 3 encoded, which is what we expect it to be. And then when you jump to the field where record encoded is, we see that's offset OXB770. And from what I recall from a few bits ago in this video, the start of record 0 is OXB70, and when you actually go to that offset, OXB770, first there are the 3 fields of record metadata, so when you actually go to offset OXB78A, we see OX31F, which is the value we expected to see there. Hello, now I'm going to run through a quick demo showing how I can edit a database file to change the information displayed when I query it. In this instance, it's going to be a pretty simple case. I will simply change it to print one string instead of the other. This demo is also documented in the documentation linked in the description of this video. So looking at the left, we see the source code for a binary. It will simply iterate through all of the records of the database, checking if the first 3 fields are equal to 0x0283, and if so, print the fourth field as a string. When we run it, we see that it will print out 2 strings somewhere in the stratosphere and have to think twice before you, because there are 2 records which meet that criteria. Now, we are going to just change this so that the second record will also point to the string of the second record will point to the string of the first record. Now, when we take a look at the actual database file, we can see that there are 2 records that go ahead and match the criteria of having 3 integers with values 0x0283. We go ahead and see that the offsets for the string are 011756 and 011776. So when you go ahead and just change this over to 011776 and go ahead and save it. and then go ahead and run it again, we see that the same string is printed twice since we changed the data to go over there. Also, one thing I'm going to say right here, there is a CRC32 checksum check that we failed. That's a part of the data integrity check. At the beginning of the database header, there is a CRC32 checksum. Now, the thing about this check is it doesn't actually appear to really do anything other than just print out the error. That's why I didn't go through the hassle of just recalculating what the CRC32 is and changing that and coming up with that bypass, since it didn't really seem to actually prevent me from doing anything that I wanted to. And also, one thing in the documentation linked, I also go over the source code for how I generated the database file. Now, since rerunning the binary for generating the database can result in reinserting the same records over and over again, that's why I just skipped over in this part of the video. Now, this alone is a pretty harmless POC since we're already seeing the same string. However, it shows you that you can edit the database, so a query operation can't output data not initially designed for it. Now, the thing is, instead of changing it over to that string, if I changed it over to data that was very important and it did not have access to typically, such as data that was created after I edited this file and it was loaded into memory, and that data was of significance to me, then this attack potentially becomes a lot more significant. But yeah, thank you for watching this demo.